The world is strange. The whole universe, from the cosmic web connecting galaxies across light years, to the frantic, probabilistic dance of particles in the quantum foam, is profoundly strange. It's a reality far more bizarre than our senses, evolved for survival on this one planet, could ever have prepared us for. And yet, here is the central paradox. When you look past the overwhelming complexity and focus on the details, the rules of the game are beautifully, elegantly simple. Perhaps no one understood this duality better than Richard Feynman. A Nobel laureate and master explainer, he had a gift for cutting through complexity. He compared the entire scientific endeavor to watching the gods play an immense game of chess. Imagine being a spectator to this divine match, but you know nothing of the rules. Worse, you're not allowed to see the whole game. You can only watch for a few moments at a time, your view restricted to just a tiny corner of the board. You can't ask the players what they're doing. All information comes from these fleeting, incomplete observations. From these scant clues, you must become a detective of the cosmos, piecing together the logic behind the movements. You watch, you guess, you form a hypothesis, you predict the next move. If you're wrong, your hypothesis is flawed. If you're right, you gain a little more confidence. This is the scientific method in its purest form, a patient effort to reverse engineer the rules of existence. Sometimes these investigations bring forth great revelations. At first, you might notice a simple pattern. A piece we call a bishop always stays on the same colored squares, a simple conservation law. But watch for long enough, and you'll discover a deeper, more fundamental rule. The bishop is constrained to move only along the diagonals. Then something truly baffling happens. You see a king and a rook move simultaneously in a maneuver called castling. This breaks your previously held belief that only one piece can move at a time, forcing you to revise your entire rulebook. The history of physics is littered with these castling moments, but it's also a story of profound unification. Time and again, what appeared to be two different sets of rules were married into one elegant framework. Like when Maxwell unified electricity and magnetism, it was like realizing two different pieces were part of the same grand design. The ultimate goal is to find the single rulebook that governs every move in the universe. But the path to this point has been an arduous one. Every time physicists have thought they were getting close to understanding all the rules, they have spotted some tiny hole in their theory that they can't explain. It's the equivalent of one of the special moves in chess, castling. As Feynman said, it's the thing that doesn't fit that's the most interesting. It has to do with curiosity. It has to do with people wondering what makes something do something. This long and winding road has delivered modern physicists to the precipice of a remarkable breakthrough. We might not need an endless list of ever more complicated rules. Instead, it is possible that all phenomena in the known universe, from the tiniest subatomic particles to all of the fundamental forces, can be explained using just one rule. That almost everything is simply vibrations in a vast web of quantum fields. But is this really the end of the game? Or are there still quirks in the rules lurking just out of reach? Thank you to BetterHelp for sponsoring this video. Everything we call real is made of things that cannot be regarded as real. The world of theoretical physics is full of moments that pull the rug from under you, and so is day-to-day life. Sometimes you need someone to help you organize your thoughts. BetterHelp is the world's largest therapy service, and it's 100% online. With BetterHelp, you can tap into a network of over 30,000 licensed and experienced therapists. Get 10% off your first month at betterhelp.com/hotttoyou, and I've also linked them below in the description. Thanks to BetterHelp for supporting educational content on YouTube. Our journey through the rules of the universe begins in the 19th century, a time of steam, steel, and radical new ideas. Cities and continents whiz by as we travel back to an era where the clockwork certainty of Newton's laws was beginning to face questions it couldn't answer. At the heart of this scientific revolution was a humble, self-taught genius, Michael Faraday. Faraday, who began his career as a bookbinder, possessed a powerful intuition that allowed him to see the world differently. Where others saw empty space between objects, Faraday envisioned it teeming with invisible forces. He introduced the concept of the field in 1846. For him, fields were not just mathematical conveniences for mapping forces. He believed they were real, physical entities, a kind of invisible scaffolding that structured the very fabric of the cosmos. You can experience this reality for yourself. Take two magnets and try to push their north poles together. You feel a tangible resistance, an invisible cushion of force pressing back against your hands. How can they exert such a powerful influence on one another without ever making contact? What is this mysterious, unseen connection that bridges the gap between them? Faraday's beautifully simple answer was that while the magnets themselves may not be touching, their magnetic fields are. He imagined these fields as a web of lines of force. When you bring two north poles together, their respective field lines point in opposite directions and press against each other, like compressed springs. This tension in the field is what you feel as the force of repulsion. Faraday's ideas were brilliant but lacked the mathematical rigor to convince the entire scientific community. That task fell to the Scottish physicist James Clerk Maxwell. In 1865, Maxwell translated Faraday's intuitive vision into a set of elegant and powerful equations. In doing so, he revealed something extraordinary. He discovered that electricity and magnetism were not separate forces at all. A changing electric field creates a magnetic field, and a changing magnetic field in turn creates an electric field. They were two sides of the same coin, a single unified entity called the electromagnetic field. This beautiful dance between electricity and magnetism meant that a disturbance in the field, a ripple, could travel outwards, sustaining itself as it went. From his equations, Maxwell calculated the speed of these electromagnetic waves. He wasn't trying to measure light. He was just using constants from laboratory experiments with batteries and coils. The answer he found was astonishing. They move at the speed of light. The number was no coincidence. Maxwell proposed the revolutionary idea that light itself is an electromagnetic wave. This single insight solved a centuries-old puzzle, explaining how sunlight could traverse the vast, empty vacuum of space to reach us from the sun, 150 million kilometers away. It didn't need a medium to travel through because the field is the medium. This discovery didn't just explain light, it unveiled a whole new reality, an invisible spectrum of electromagnetic radiation that underpins the modern world. Yet, at the turn of the 20th century, cracks began to appear in this classical worldview. Physicists were baffled by a problem known as the ultraviolet catastrophe, where existing theories predicted an impossible infinite energy emission from hot objects. The first hint of a solution came from Max Planck, who proposed that energy wasn't continuous, but came in discrete packets or quanta. This idea was radical, but the most damning evidence against the old rules came from the photoelectric effect, the observation that light could knock electrons off metal. Something was fundamentally wrong. In 1905, Albert Einstein took Planck's idea and argued that light itself is a stream of these energy packets, fired like bullets. Each particle, which we now call a photon, carries a specific amount of energy. This perfectly explained the photoelectric effect. A single photon either has enough energy to eject an electron or it doesn't. It's an all-or-nothing collision. Turning up the brightness just means firing more bullets, but if each is too weak, nothing happens. It was a breathtakingly simple and powerful explanation. This led to a truly bizarre conclusion. Light was somehow both a wave and a particle. It travels like a wave but interacts like a particle. Scientists soon discovered that electrons, and indeed all matter, exhibited the same schizophrenic nature. This discovery didn't just change the rules of the game, it revealed that the chess pieces themselves were not what they seemed. The classical game, with its solid, predictable pieces, was over. This quantum weirdness governs everything, including you. It seems undeniable that you are currently touching the chair you're sitting on, but according to the rules of this new game, you aren't. The atoms making up your body are mostly empty space, surrounded by a cloud of electrons. As the electron clouds of your body approach those of the chair, they repel each other with incredible force. This repulsion creates the sensation of touch, so you are, in a very real sense, floating, levitating an infinitesimal distance above the chair on a cushion of force, supported by a swarm of subatomic specters. But the revolution didn't stop there. The final mind-bending step led to quantum field theory. This theory proposes that the most fundamental components of the universe are not particles at all, but fields. Vast, invisible fields that permeate all of space and time. What we perceive as a particle, like an electron, is simply a localized vibration, a ripple in the electron field. A photon is a ripple in the electromagnetic field. Each fundamental particle has its own corresponding field, layered on top of each other everywhere in the universe. Everything you see, everything you are, is a complex symphony of these vibrating fields. The universe is not a stage with actors on it, it is a grand, interconnected dance. The fields vibrate, and those vibrations, what we call particles, interact, creating the illusion of a solid world. This is the ultimate reality of the gods' game of chess, where the board and the pieces are one and the same, woven from the same fundamental, vibrating fabric of existence.